So what aspects do we have to consider if we want to define a protection scheme? So you already realize there is a strong relation between protection and the network. That means we have to look a little bit into the network. And the first question is, of course, what type of component do we want to protect? This picture just shows a mixture of all the different components which may be available in the network. Of course, the majorities are lines and cables, transformers. What you also see here is generators, motors, and other special things. Bus bars is also important. The focus here in this introduction will mainly be on network components. That means transformers, bus bars, cable, and lines. The focus will not be generator protection and motor protection, because there a lot of different things have to be considered. So one thing is the type of component. The next thing we have to look at is the voltage level. This starts from the extra high voltage level, from the transmission network level, and it depends on the country, on the area of the world where we are, which voltage level we find there. It can be something between 220, 400 kilovolt, 750 kilovolt, or trials are already done with even higher voltages. The voltage level which is used depends on the size of the country, the distances, and the amount of energy we have to transport. Always remember, for the protection relay, the voltage level doesn't make a big difference because the voltage is always transformed down to that level which is seen by the relay. But the concepts to do protection are different in high voltage level compared with medium voltage. Below high voltage, you have typically so-called subtransmission level. Also there, the voltages are different in different areas, 110, 132, or 150 kilovolt. And below that, you have a medium voltage level, which does really the distribution of the energy into the cities, the villages. These are often cable systems, but it can also be overhead lines like shown in these pictures. And the voltage levels we cover here with this technology starts typically from 6 kilovolt up to, for instance, 30 kilovolts in the medium voltage level. That are the voltage levels. We also have to look into the network structures, and they depend a bit on the voltage level. What you see here is a mesh network. That is what you typically find in transmission systems and subtransmission systems. That means we have a mesh system which has grown somehow, which connects the power station, the generation, and the loads. That means the transformers you see here connect the power station to the grid, and they can also be connections from these transmission networks to subtransmission or to distribution. Important thing here that is important for protection is we have a meshed structure. That means if we have a short circuit somewhere on one line, the current comes from different sides from different directions into our line. And that is an important fact to define the protection. Another type of network is shown here. That is a typical network we often find in distribution systems. We have one bus bar, which gets its energy from in-feeding transformers. And then from the bus bar, we have so-called radial feeders. That means feeders with different substations, transformer stations in between. And these transformers transform then down from the distribution level, 20 kV, down to the low voltage level, 0.4 kV. And the important thing is that these feeders are radial. That means on the bottom here, these connections are open. That means we have a system with no meshes. The system is radial. And the important thing is, if you have a short circuit on one cable, for instance, on this cable, the short circuit current comes through the transformer, the bus bar, to this cable. It comes from one side, and that is a very important feature when we design the protection system. You may ask the question now, why do we have these strange connections here on the bottom? The reason is the following. Imagine you have one cable destroyed, for instance, by street work. In the moment the cable is destroyed, you typically have a short circuit. Then the protection will disconnect this cable to remove the short circuit. But then the bottom transformer here is without energy. And what you can do then is you can remove the destroyed cable from the network and then close this connection point here on the bottom and resupply this transformer here through the connection from the other side. That means normally you have a radial system, and we will see that's important for protection. After protection has worked, you can reconfigure the system. That will take some time, depending whether you have remote control or you have to drive there to reconnect that. Important point here is normal operation is a radial system. Similar things are normally visible in industrial systems, like shown here. These systems are often also radial. The difference in comparison to the public distribution systems is that here the distances are normally shorter. So we are here within one plant, chemical plant or refinery. Distances are shorter, and we normally have a lot of motors involved here. But also there, the main question for protection is, do we have meshes or is the system a radial system? That was the system structure. The next point we have to consider is the neutral earthing. And that is a point which has really big impact on protection. What we see here is the one side of a transformer in the system, and this transformer has a star point. And now the big question is, what do we do with the several star points in the system? One thing you can do is so-called solid earthing. That means you connect the star points to ground. And that is what you typically do in transmission systems. There normally the star points are grounded. What does that mean? That means if you have a short circuit, a single phase short circuit, or if you have a connection to ground, which is the most probable type of short circuit, then you have really a short circuit loop here. And that means if you have this type of fault, connection of one phase to ground, you have really a short circuit with a big short circuit current. If you want to reduce the short circuit current, you can add a resistor here in the star point. If you again imagine this connection to ground and look at this short circuit loop, you now have the resistor in this loop. And that means by this resistor, you can limit the short circuit current. And for some cases, especially in distribution systems, this is done. Because for the most probable type of fault, you have then a reduced short circuit current, which means the risk of damage, of injury of people, and so on is lower. But that refers only to phase-to-ground fault. That does not influence the short circuit current in case of a phase-to-phase fault. And you can do even more things. You can put in a reactance here. And with such a reactance, you can bring down the short circuit current even to 0, or you can leave this open. That means in such a case, if you have such an arrangement, if you have a reactance here or if you have the star point open, you have pretty low currents. In case of a phase to ground fault, you can even continue operation without risk of damage. So the earth fault in this case is not really a short circuit because there's only small current flowing. That's the good thing. But on the other hand, you must find that fault. You can continue operation for seconds, even for minutes, but you must find this type of fault. That means in such a case, you must have additional protection functions to identify and to look to find out where this type of fault is. So that is a special area of protection in these networks. That means if you think about a protection system for a network, you must have a look at this star point treatment. As I said, transmission system, you are typically with solid earthing. In distribution and industrial systems, you find a lot of other different things. That was the neutral earthing. And the last thing I'd like to mention is here, what types of fault do we have to consider? On the left-hand side, on the bottom, you see the most frequent type of fault, single phase to ground fault. This will occur typically, for instance, if a lightning arc hits an overhead line. You have an overvoltage there, you get a flashover on a tower, and then you have a phase to ground fault. And you can assume that roughly in an overhead line system, roughly 80 to 90% of all short circuits are single phase to ground short circuits. Sometimes they evolve to a phase to ground fault. That means if you have on one tower a lightning arc burning, a short circuit burning on the tower, there's a lot of hot air flowing around there, and that sometimes affects also another phase. Then you get this phase to ground error fault. And of course, you can also have just a short circuit between two phases. For instance, if the conductors of an overhead line start some oscillations. And of course, there is also a risk of a three-phase short circuit. That is not very often. A typical thing, for instance, would be in a distribution system. You have roadworks there, people opening the street, didn't look at the cable plans before, excavator hits the cable, and either you get an interruption or you get a short circuit, or both. That's one reason why you have three-phase short circuits. Another reason can be you did maintenance on a line. If you do maintenance on a line, you have to ground the line. That means you have to connect all the three phases together to ground. Then you can work on the line. After you have finished your work, you want to reconnect the line. And if you then forget that the grounding is still there and energize the line, you have a three-phase short circuit and the protection has to trip. So that are the types of short circuit. On the right-hand side, you also see other types of faults like interruptions. They are not so critical normally. A three-phase interruption means we have no longer transport of energy. The other side is maybe without voltage, but it's not such a critical thing that something explodes. But if you, for instance, supply a big motor in a chemical plant, for instance, and you have a single-phase interruption, a motor doesn't like that, or a generator, because these motors and generators need a three-phase system to have a constant torque. And if one phase is missing, you can destroy the devices. So for that reason, also these types of faults have sometimes to be connected, disconnected. So we come to the end of this chapter. We looked at the different aspects of the network, which have to be considered to bring together a protection scheme. And in the next chapter, we will look at the protection principles which are available to detect short circuits.